Welcome. In this chapter we're going to learn about the physics of the ocean circulation and the forces that drive it. We're going to ourselves ask the question, how has the ocean circulation been discovered and measured, what drives this, and what are the forces behind it? Ocean currents are important because you can think of them as the giant rivers of the ocean that transport substances like heat, temperatures, and CO2 across the system. Captain Hunter Brown of the Glasgow School of Navigation released about 2,000 bottles in June of 1914 to discover the circulation pathways of the North Atlantic. About 100 years later, one of those bottles was found, and you can still take witness on how ocean circulation was discovered and measured in the early days. About 30 years ago, a big storm in the Pacific Ocean caused a container ship to get into trouble and lost some of their containers. Inside some of those containers were rubber ducks and also Nike sports shoes, and they were drifting with the ocean currents and the wind, but largely the currents, through the Pacific and washed ashore in the Pacific west coast of the United States. Beachcombers found those shoes and rubber ducks, and a colleague of mine took note of where they washed ashore and when, and also got an idea of how the ocean circulates. In more modern days, we are concerned about all the plastics in the ocean. And if you take a closer look at an animation of how the plastics move throughout the system, you will find out that somehow they magically gather up in these, what we call these ocean gyres, and they form big plastic garbage patches. And the question is, why do these things happen? Now, ocean physics help us there. As the wind blows over the ocean, you see that this ocean starts accelerating, but because the Earth is spinning very rapidly, the surface currents don't move exactly down the wind, but they actually turn at a particular angle. At the surface, it's 45 degrees, but if you average over the upper 100 meters of the ocean, it actually moves at the right angle of the wind speed, which is pretty fascinating. Now, if you put that knowledge together, you have the west winds moving across the ocean gyres, and the Ekman transport, the upper ocean transport, moves all the materials to the south, while in the southern areas, the trade winds in the Ekman transport moves them to the north. So what that means, in the middle of the ocean, you have this convergence, and the convergence gives rise to the sea level, and so ocean water converges there and then gets pumped down. Now guess what? Plastics, fisher nets, and rubber ducks gather up there. They can't sink down, so they just keep collecting. So that's how you create these garbage patches in the middle of the ocean. From a physical point of view, that high sea level then exerts a force. The water wants to go back to the lower sea level, and again the rotation comes to play, and we have the ocean circulation circulating around these high stands, giving you what we call ocean gyres. These big ocean gyres are the main current system of the ocean. They connect the Gulf Stream, North Atlantic Current, Canary Current, and North Equatorial Countercurrent, and these gyres happen in all ocean basins. We have a gyre in the North Atlantic, in the South Atlantic, North Pacific, South Pacific, and also in the Indian Ocean. And these surface currents are really important because they drive things throughout the system, and they also connect ocean basins. On the other hand, when you think about the temperature of the ocean, which is warm in the tropics and cold at high latitudes, the temperature controls the density of the ocean. In cold areas, water sinks down to great depths, and by that we can also cause an ocean current. It's not the horizontal one, it's a vertical ocean current. Cold water sinking down, slowly warming up and coming back to the surface. This gives rise to a circulation that we call the meridional overturning circulation. So it's driven by the coldness in the poles, and it's supported by the upwelling throughout the ocean basins. This large-scale circumnavigating sets of currents is sometimes called the global ocean conveyor belt. So what that means is that this large-scale temperature-driven ocean circulation connects all the ocean basins to each other. It takes the cold water, moves it to the south, to the milder climates of the tropics, but it even then keeps going to the southern hemisphere and slowly comes back up in the Pacific Ocean, Indian Ocean, and returns as a warm current back to the polar regions of the Atlantic. So this circumglobal current system, I think, gives you a good indication why we like to talk about one ocean, because the ocean circulation connects all ocean basins and gives rise to one ocean system. Both the wind-driven horizontal circulation and the density-driven vertical overturning circulation are important to understand the ocean system. They move nutrients, temperature, salinity, and carbon throughout the system, and really show you how the ocean currents are so fundamental to understanding the ocean climate system. Ocean currents can be measured and observed these days, rather precisely also from satellites, and it allows us to understand how they evolve over the next couple of hours, over the next couple of days, and give us some predictive power to advise mariners and seafarers. The fate and the change of ocean circulation on longer timescales is more complicated. They're actively researched in the climate and ocean community, and we're trying to really decipher how a changing climate will affect this temperature-driven overturning circulation of the ocean and the transport of nutrients, carbons, and oxygen throughout the system. It's still a challenge for us in the community, but one thing is clear: the ocean circulation connects all ocean basins, and that's why we like to talk about one ocean.